What if for a moment you thought of a world where neither you, your family, nor that person who served you at the supermarket existed? Imagine a place without grand art, without stirring music. A world where hunger and the horrors of war should never have happened. Let's go further. What if not even the universe should exist? Let's start from the beginning, with the Big Bang. An event so unlikely that the chances of it occurring were 1 in 10, raised to the power of 10, raised to the power of 123. A number sometimes called the Penrose number, in honor of the British physicist and mathematician Sir Roger Penrose, a Nobel laureate. This number measures the incredible level of order and precision with which our universe was created. But as we know, order and precision tend to decay over time. You've seen this happen with the wires of an old pair of headphones, which get more and more tangled, or in the crumbling ruins of an ancient city, where magnificent buildings carved thousands of years ago by our ancestors are reduced to dust and rubble by the passage of time. Penrose knew that our universe should behave in the same way, with its order and precision decaying over time, just like the cities of ancient Egypt, China, and Mesoamerica. He knew that black holes were the crumbling ruins of the cosmos, the place where everything eventually ends, where order and precision finally yield to the abyss. There are still about 10 raised to the power of 80 protons, neutrons, and other similar particles scattered throughout our universe, still avoiding the abyss of black holes, still clinging to their order and precision. This makes our universe special, like an ancient artifact that has not yet disintegrated into dust. And when Penrose did the calculations, he realized that our universe must have been sculpted with a level of precision that simply didn't make sense. Incredibly low entropy, a chance of 1 in 10 raised to the power of 10 raised to the power of 123. And this impossible number is not alone. Antimatter is like the mirror image of matter, and when the two combine, they mutually annihilate. And although there are 10 raised to the power of 80 protons, neutrons, and other matter particles in the universe, there was only a pinch of antiparticles. Thankfully, because if there had been an equal number of particles and antiparticles created at the Big Bang, they would have annihilated almost instantly. And yet, nothing in our best models of the universe seems to give enough preference to matter over antimatter. Indeed, when we extrapolate the results of experiments, it seems that the universe should have been born with an equal amount of everything. Everything should have been annihilated. You and I should not exist. The universe should not exist. And yet, it does. But there is one prediction that worries physicists more than the lack of antimatter or the ordered state in which the universe was born. It's the weight of the universe. When theoretical physicists put quantum mechanics alongside general relativity in a controllable way, they discover that the universe should have folded in on itself at the moment of creation, should have been crushed by an overwhelming weight, most of which does not come from the planets and stars scattered across the galaxy, but from empty space, from the vacuum. Our entire universe should have been crushed by the weight of nothingness. This is a mystery known as the cosmological constant problem, which has haunted physicists for almost 100 years. Have you ever wondered why the blood in our veins is red? Julius von Meyer, a ship's doctor on expeditions to the Dutch East Indies in the 19th century, made a remarkable discovery while treating sick sailors. In the full sun of Indonesia, he observed that his patient's blood shone with a more intense red than usual. Back in Germany, the blood always seemed darker. And why? The answer was in the temperature. Von Meyer realized that, under the tropical heat, the sailors' bodies didn't need to burn as much fuel, read food, to keep warm. Result? Super-oxygenated blood and visibly redder. And then he had an epiphany. Body heat is like the heat of the sun, both a form of energy. But wait, what exactly is energy? Thinking about this, our journey takes us to the past, to the 18th century, when the first industrialists sought ways to transform trapped energy into useful work. The ancient water wheels and revolutionary steam engines are perfect examples of how energy can be transformed into motion. And speaking of transformation, Albert Einstein brought a new light. Mass is also energy. Using this idea, Einstein developed the famous equation E=mc². And when we talk about weight, it's not just about how many pounds heavier we are after the holidays. It's about gravity pulling on every form of energy, even light. So, when a physicist asks how much you weigh, he's really talking about how much energy exists in you and around you. In the city of Syracuse in the 3rd century, BC lived Archimedes, perhaps the greatest mathematician of his time, studying the size of the universe. Imagine yourself beside him, questioning, "What if I told you that the number of grains of sand is not infinite?" Archimedes was not convinced that the universe could contain an infinite number of grains of sand and began to calculate how many could actually fit. He started his experiment with poppy seeds, lining them up side by side. About 40 of these seeds are approximately 0.75 inches. Within each seed, Archimedes imagined myriads of grains of sand, a myriad being 10,000, the largest unit he knew at the time. With this scale, he challenged himself to invent a new numerical system to count all these imaginary grains and even estimate the size of the universe. With cunning reasoning and simple estimates, Archimedes concluded that the sphere of the universe, centered on the sun and extending to a mantle of fixed stars, had a diameter of approximately 100 trillion Greek stadiums, or about 2 light years for us. All in all, he concluded that the universe could not accommodate an infinite number of grains of sand. The number would not exceed 10, raised to the power of 63. But wait, how much would a universe full of sand weigh? Well, Archimedes wasn't really concerned with that, but imagine that each grain of sand weighs about 0.01 grams. His sand universe would weigh something around 10 billion trillion pounds. Strangely, this calculation was not so wrong, but it was just a stroke of luck. Archimedes massively underestimated the actual size of the universe. And now, if we really want to take the weight of the universe seriously, we need to stick to the observable part, which extends for 46.5 billion light-years in all directions. When we start to weigh the universe, we don't just consider stars or planets, but also the mass of other sources, like interstellar gas. A better method to measure the mass or energy of the universe is to study its effect on the shape of space-time. Observations of the cosmic microwave background, the primordial photons left since the formation of the first atoms, reveal that the observable universe contains about 150,000 trillion kilograms of mass. This sounds like a lot, but in fact, the matter we can see represents only 5% of the total energy. There are 2 more ingredients that dominate the universe: dark matter and dark energy, which together make up 95% of the universe. Dark matter, although 5 times more abundant than visible matter, is still not the dominant ingredient. That honor goes to dark energy, responsible for 70% of the universe and for pushing its expansion. So, what is dark energy? All data points to an exotic substance, whose energy density is virtually constant throughout the universe. And, as we'll discover, this is exactly what you'd expect from the energy of empty space. Now let's imagine we're aboard a weather plane in 1949, flying from Japan to Alaska. A simple piece of filter paper detects alarmingly high levels of radioactivity. This event triggers a sequence of analyses until, on September 23rd, US President Harry S. Truman announces that the Soviet Union had detonated an atomic device. The detonation occurred a few days earlier, on August 29th, at the remote Semipalatinsk test site in present-day Kazakhstan. Now, visualize 10 kilometers south of the epicenter. Yakov Zeldovich and 7 other men witness a nuclear explosion. Imagine the scene: a bright flash, followed by a tongue of fire tearing through the dust and smoke sky. While some celebrate, praising Stalin, Zeldovich remains silent, perhaps contemplating the implications of what they had just witnessed. Zeldovich was not just a spectator. He was a super Soviet physicist, making significant contributions not only to nuclear weapons, but also to particle physics, astronomy, and cosmology. Decades later, he would stand out again, this time with his theories challenging our understanding of the universe. Now, think about the cosmological constant, a problem that Zeldovich brought to light in the 1960s. This constant, a measure of energy in the vacuum of space, challenges quantum theory and general relativity. The universe itself seems to contradict its catastrophic predictions. How is this possible? Here enters the idea of the multiverse, a solution that suggests the existence of countless universes, each with its own laws of physics. Perhaps in some rare corner of this multiverse, things balance out in such a way that life is possible. And curiously, we are exactly in one of these rare universes, where everything is just right for the formation of stars, planets, and complex life. In addition to being intriguing, this discussion about the multiverse and the anthropic principle might seem a bit above our everyday reality. In a way, each of us is a small universe of possibilities, trying to understand the grand scheme of things. Before you go, don't forget to like and subscribe. So, what do you think about all this? Comment below, see you next time, and stay curious.